My name is Mike. I've been playing baseball since I was 8.
My name is Matt, and I've been playing baseball since I was 7.
My name is Bobby, and I've been playing baseball since I was 6. My name is Joe, and I've been playing baseball since I was 5.
Today, me and my group members will be discussing the physics of baseball. Alright, today we will talk about the physics of baseball and unknown parts to the average person. Baseball may seem like a boring sport, however, there's a lot happening. As fans of the game, we are interested in analyzing and learning the physical aspect of the game that we grew up watching. Such things as pitching, hitting, we will be analyzing and demonstrating throughout this TED Talk.
Also, as players of the game, I believe that the topic could possibly help our development of the game. And hopefully, one day, we can use this to learn how to throw hard.
In this demonstration, Matt's going to do the physics behind pitching.
Hold on.
In this demonstration shown, Matt is pitching from the mound. As he goes through his windup and stretch, he begins to release the ball. The ball travels its course until caught by Bob.
In this demonstration, Bobby's going to be showing the physics behind hitting.
As the ball approaches, Bobby is going through a swing process until making contact with the ball.
As a pitcher is going through his motions, he reaches a throwing point where the pitcher's arm is undergoing a great amount of pressure. There is approximately 100 newton meters of torque on a pitcher's arm during a pitch, equivalent to a 60-pound weight hanging from his hand. The stress on high-speed throwing pitchers is detrimental and can lead to arm injuries in the future if using bad mechanics. Some injuries may be Tommy John surgery, which is the ulnar collateral ligament being torn and therefore can either help or hurt that pitcher's career. When released, the ball undergoes multiple forces: rotational force, gravity, air resistance, and the force applied. When the ball is thrown, it also undergoes Bernoulli's principle. On the mound, there's a number of pitches to choose from, ranging from the fastball to the changeup to a curveball or even a knuckleball. When a curveball is thrown, it is given a lot of topspin, making it drop. What this means is that there's a higher air resistance on the top of the ball and a lower air resistance on the bottom of the ball, giving it that drop effect. With different grips on the ball, it creates a different spin. Changing the spin also changes the air resistance on the ball, making it move from left to right or up and down. The famous knuckleball pitch is known for its ability to defy physics. The reason this happens is because the pitch makes about 1.25 revolutions on its way to the catcher. Due to the lack of spin, the ball becomes aerodynamically unstable. The raised seams along the ball create an uneven flow of air over the surface of the ball, causing the ball to move side to side or up and down. By using your knuckles and pushing the ball at the release point, this causes the ball to have less spin. What's different about this pitch is that the movement of the ball tends to go anywhere at any given point in time, making it extremely hard to hit and very unpredictable. While most of other pitches, hitters have a time to adjust and see where the ball will meet its bat. At low speeds, when throwing off-speed or breaking pitches, there is turbulence occurring along the back of the ball. This turbulence then turns into a smooth flow, helping the ball break in different directions. For example, a curveball. When throwing at high speeds, there is turbulence in the front of the ball. Once the turbulence smooths out, this allows the ball to cut through the air faster, increasing its velocity. For example, a fastball. The ball itself has red stitches, in this case, white stitches all around it. These stitches play a much bigger role than most people think. A ball that is smooth has more drag, making it travel slower and not as far. So picture a ball with no stitches or leather covering it. This means that the ball has more drag, creating less velocity and less distance. The red stitches on a baseball help cut through the boundary layer of air around the ball. This allows the ball to have more turbulence in circulating around it and causing the ball to spin more, creating more velocity and a greater distance.
Watching the demonstrations of us hitting the baseball, I will now further discuss the physics behind hitting. Hitting a baseball has been said to be one of the hardest things to do in any sport. Using the barrel of the bat, or so-called sweet spot, is the ultimate goal of all hitters of the game. When the batter comes in contact with the baseball, there are vibrational waves that travel throughout the bottom and top parts of the bat. The one specific spot in which the vibrations created from the ball striking the bat cancel each other out. Therefore, there is very little energy that is lost after making contact, thus allowing the maximum amount of energy to be transferred to the baseball and allowing it to travel. The batter can tell when they have come in contact with the sweet spot of the bat because there is no sting sensation that goes throughout their hands. The batter will feel almost no sting at all. What makes this objective so difficult is that the batter must hit the baseball within an 1/8 inch of the sweet spot in order for it to travel the maximum distance possible. Now, as the bat travels through the strike zone, it is on its way to demonstrate Sir Isaac Newton's second law of motion, which explains that the force exerted on an object is determined by its mass and acceleration. As the ball approaches the batter, the mass and acceleration of the bat creates a force that projects the ball out onto the field, whether it is the infield or outfield. Now, Newton's first law of motion is also demonstrated while batting. Newton's first law states that an object at rest remains at rest, and an object in motion stays in motion. When the pitcher releases the ball, it is in flight and wants to continue in flight, but is then acted upon another force, also known as the batter or catcher. Now, as the batter squares up to hit the baseball, there are two possibilities. The first possibility is the catcher catch the ball, ending the play with Isaac Newton's first law of motion. Or the batter can hit the ball, reinstating Isaac Newton's second law of motion, and then reinstating Isaac Newton's first law of motion, which then ends the play. Now I will explain how work is being done in the aspect of hitting a baseball. Once the bat strikes the ball, work is now being done. When the batter comes in contact with the baseball, work is then being done on the bat, therefore the bat is doing work on the ball. In physics, work energy can be transferred into heat energy. Therefore, at the moment of contact, the ball is being warmed up, causing it to deform. At the point of contact, the baseball begins to flatten, but is not able to be seen by the human eye, thus needing a slow motion camera to see the deformation of the baseball. However, what is really happening is that work energy is being transferred to the ball, in which allows the baseball to be projected onto the field in any spot on the field, including infield or outfield. Before the presentation, the batter is trying to make contact on the sweet spot of the bat, which is approximately here to here. At the point of contact, heat energy is conducted and transferred to the ball, causing it to deform. For example, if you can see this, bring it a little closer. The ball indents and then repels off the bat. Newton's second law is then shown by the massive acceleration and the bat creating a force to project the ball outwards.
The physics of baseball can be applied all around us, not just in baseball.
Isaac Newton's third law of motion and aerodynamics, among other topics, are used throughout everyday life.
Air flight, as well as projectile motion situations, can relate to baseball throughout aerodynamics.
This topic can be useful to anybody who's interested in engineering or anything like that.
And Newton's third law can be seen just about anywhere, ranging all the way from a rocket lifting off to someone pushing a car off some ice.
As Matt mentioned earlier, in the demonstration, he stated how there's multiple forces acting on a baseball as it travels through the air. This same example can be applied in air flight. As the plane takes off, there are multiple forces acting on it. For example, lift, drag, thrust, and gravity. Drag is something that affects a baseball's velocity. In comparison, drag also affects the speed it takes for a plane to lift off. As the baseball travels, there's also turbulence occurring behind and in front of the baseball, depending on what pitch is thrown. As it continues, the turbulence smooths out and cuts through the air much more faster and easier. The same idea happens when a plane experiences turbulence. However, the wings help cut through the air much forward faster, like the stitches on the ball.
When it comes to hitting a baseball, there are two different laws of motion occurring. When the pitcher releases the ball is in constant motion. This demonstrates Newton's first law of motion. As the batter makes contact, he is applying an opposing force, putting the ball at rest. An example would be a bunt. A real-world situation demonstrating Newton's first law would be workers using a crane to build a steel frame of a building. The steel beams are at rest and remain at rest. While the crane applies a force to the beam to lift it, the beam still remains at rest. Newton's second law states that the force applied equals the mass of an object times its acceleration. As a batter makes contact, the force of the bat on the ball equals the bat's mass times its acceleration, projecting the ball outward. When building a house, a laborer must hammer nails onto the roof. The force applied to strike the nail equals the mass of the hammer times its acceleration.
Next installment of TED Talk, we will talk about the sport of hockey. Like baseball, hockey uses the amount of torque a player provides from his lower body to transfer the energy to the puck. Hockey uses much of the same physics that are used in baseball, such as aerodynamics, Newton's first, second, and third law. Hockey's similarity with hitting a baseball is almost identical to hitting a hockey puck, but with two different types of shot, the slap and wrist shot. The wrist and slap shot both have different velocities after being struck, such as a baseball player at bat hitting for contact and a baseball player at bat hitting for power. To further explain the similarities of aerodynamics between the two sports, the grooves on the puck help break the boundary layer of the air, allowing it to have a higher velocity, and that's like the stitches of a ball on a baseball.